Okay, welcome back. Hope your midterms went well for you. Our next subject, following comets and asteroids, which has also been posted now. I hope you will take a look at that, because that will also be on the next midterm. We're finally going to get to the sun. So the sun is by far the most dominant object in the solar system. Something like 99.9% of all the masses of the solar system is in the sun. So what that means then is that we've been studying 0.1% of the solar system for the last few weeks. And so this then are the planets, moons, comets, and asteroids. Just 1/10 of 1%. And so it seems like we should be spending a lot of time talking about the sun, because this is a very important object in terms of its size. And we mentioned this before. The size of the sun is something like 100 times the radius of the Earth in terms of the radius. So that means that if you had the sun like this, you could put 100 Earths across the sun at the equator. But that doesn't mean that the sun is 100 times bigger, because in terms of the volume, it goes like the radius to the third power. So we have something like 1.3 million Earths would fit inside the sun. As a matter of fact, if you were put the Earth at the center of the sun, which wouldn't do it any good, but let's just imagine we could do that, and you wanted to fly to the moon, you'd have to fly essentially twice the distance from the Earth to the moon just to get out of the sun. That's how big the sun is. It's something like twice the distance from the Earth to the moon. Okay? And so the sun is gigantic. You fit 1.3 million Earths inside the sun, so that's how much more volume the sun occupies. And it's also the center of gravity for the solar system. And so without the sun, we wouldn't get the energy that's necessary for life. Say, well, how else could it be? If you had a planet, it's got to be going around a star, right? Well, no. When we look in the galaxy, we believe that there are about as many planets that are rogue planets that aren't orbiting around stars as there are planets that are orbiting around stars. So the Earth could have easily been kicked out in the early solar system when there was that jostling for position. So without the sun, this could just be a frozen slag heap here for the Earth with no life-giving energy. And this also creates a gravitational center for the planet's orbits. So we would have no life-giving energy without the sun, and the sun is providing this source of gravity that makes our orbit around the sun stable and allows for energy to flow into the Earth. And so that energy that flows into the Earth, then molecules have adapted in such a way as to turn into life because of this energy that has been injected into the Earth because of the sun. Okay, and so we might then, if we look up at the beta projector for a second, we see then that, well, here's the sun, and we see some little spots on it. Those spots are about the size of the Earth. Those are actually cool spots that we'll talk about later called sunspots that are on the surface of the sun. Now, what's the source of the energy? Well, what makes the sun the size that it is what's called nuclear fusion. That happens in the core. Now, this term fusion is oftentimes confused with fission, which is the source of energy, say at Diablo Canyon or at any kind of nuclear power plant, and is the source of energy for an atomic bomb. Whereas fusion is the source of energy for a hydrogen bomb. And in fusion, as the term suggests, atoms are fusing together. And so here we have 4 hydrogen atoms turning into 1 helium atom plus energy. This is our fusion, this is our hydrogen fusion reaction. And what it tells us is that if you have 4 hydrogen atoms, which are basically just protons, because the temperature inside of the sun is so hot that the electrons are torn off. So you don't have electrons, basically. You have what's called a plasma inside of the sun. So these 4 hydrogens under intense enough heat and pressure can turn into 1 helium atom. And in the process of doing that, energy is released. Okay? And so if we were to look at this in a nuclear physics class, what we would see and what we would study would be this kind of a reaction. On the left, we have those 4 protons, and then there would be an interaction that would create heavy hydrogen, which is deuterium, and then those deuterium atoms would eventually become helium-3, and then 2 of the helium-3 atoms would eventually become a helium-4. That's really much more detail than we need here to understand this. But the important thing to get out of this reaction, 4 hydrogen goes to helium plus energy, is that if we were to take the 4 hydrogen atoms and put them on a scale, they would weigh more than 1 helium atom on this side. So on this side then, the 4 hydrogen atoms weigh just a little bit more than the 1 helium atom. And that difference is converted to energy. So this is about 0.01 or 1% of the mass converted to energy. So this is 99% of this mass. This is 100%. This is the original mass. But when it's turned into helium, you only have 99% of the mass left. And that 1% is converted into energy. So we might then wonder, well, if only 1% is converted into energy, is that really that big of a deal? Doesn't sound like it. But it is because of Einstein's famous equation, E equals mc squared. Here, m is the 1% of the mass that's converted to energy. And even though this doesn't seem like very much mass, when we multiply it by a really big number, speed of light, and then square it, we get a lot of energy. So this is a bit. So what this really tells us is that mass is a concentrated form of energy. If the speed of light weren't very big, then E equals mc squared might not be such a big deal. But because the speed of light is a very large value, we get a large amount of energy, even from a small amount of mass. And so what happens then is and this only happens in the core, where the temperatures are hot enough. And so the core temperature in the sun is something like 27 million degrees Fahrenheit, or about 15 million degrees centigrade. And so it turns out that that's the kind of heat you need to turn hydrogen into helium. So you can't just do this any old place. And we've tried to do this on the Earth. It's called cold fusion, and it has failed. That doesn't mean that we'll never be able to figure out how to make fusion work on the Earth, but we've spent so far billions of dollars trying to, and basically so far we've just been throwing our money away. We haven't gotten any closer to a good source of hydrogen fusion on the Earth. But in a star, nature has it figured out pretty nicely, because these hydrogen atoms with high enough temperature means that they can move toward each other very rapidly. That's what temperature is molecular motion. And so the H atoms can move toward each other fast. And they can get close enough to each other so that something that's like little hooks can engage. Now, there aren't really little hooks on the hydrogen atoms, but you can think of these hooks as representing what's called the strong nuclear force, which is the force that binds together atoms in the nucleus. And so if you can get the hydrogen atoms close enough to each other so that those hooks can engage, then the strong nuclear force, which is only very short range, indicated by the short length of the hooks, that can only happen when the temperature gets high enough. And so this is why there's only fusion in the core, because the core is where the temperature in the sun is the largest value that it's going to be anywhere else in the sun, because of all of the weight pushing down on the core, heating up the core and generating very high pressures as well as high temperatures. Okay, and so it's just like with a match. If I tell this match, come on, light, nothing, don't get it. But if you strike the match, you give it the energy of activation. And then you can get a self-sustaining reaction, which is fire. In this case, our nuclear fire is gotten from a self-sustaining reaction when the core temperature can get hot enough so that those hydrogen atoms can get close enough to each other so that their little hooks can engage. And that's what gives us the conversion of the 1% of the mass via hydrogen fusion. That's converted into energy. Now if we look again at the data projector, what we see is a balance. This is what we call hydrostatic equilibrium for the sun. Because the sun has two forces that are acting. One force is the outward force due to nuclear fusion, and the other is the inward force due to gravity. And so when those outward and inward forces are equal, then we have what's called hydrostatic equilibrium. Now we know gravity is a force, obeys the inverse square law. We know that the fusion takes place in the core. So that's the source of our fusion reaction, is the core. And so we reach equilibrium then when the outward forces equal the inward forces. That happens when the gravity forces equal the outward fusion forces. So this is a very natural process then. As a star forms, it forms from, at first, gravitational forces acting, but it's not hot enough for fusion yet. Until finally you get to a more compact state in which the temperature can go hot enough, and then you light the fusion reactor, basically. And that fusion reactor then pushes outward, but maybe not hard enough to overcome gravity. And so gravity pulls in even tighter, and that cranks up the fusion engines even harder, until finally the fusion forces and the gravity forces are just equal, and then it balances out. And so that's the reason why a star reaches an equilibrium state that is a balance between these outward forces of fusion and the inward forces of gravity. And so that gives rise then, in the case of our own sun, to a conversion of hydrogen into helium. We have 400 million tons of hydrogen are converted to helium every second. Every single second inside of our sun, 400 million tons, think about that, 400 million tons of hydrogen are converted into helium. And so you'd think that the sun would run out of hydrogen gas. Just like a car would run out of fuel if you're burning up the fuel at that rate. But it turns out that if you multiply this 400 million tons per second by the number of seconds in, say, 10 billion years, you only get a few percent of the hydrogen is used up. Just a few percent. The sun hardly even notices that over 10 billion years, just because the sun is so massive. And so of this 400 million tons of hydrogen that's converted to helium, 1% of that is converted into energy. And so that means about 1% of 400, or 4 million tons of mass, are converted to energy every second. In the sun. So that means the sun is getting lighter by 4 million tons a second. It's also ejecting off as the solar wind about 1 million tons of particles per second as well. And during some events that are more energetic, like a solar flare, could be as much as 1,000 times larger than that. And so the sun has many ways of losing mass, but it's just kind of a drop in the bucket for the sun. The sun hardly even notices these changes, even over billions of years, because of the sun's enormous size. And so the next thing I wanted to look at is the interior structure of the sun. So we can go back and look at the data projector real quick here. And we can see the cross-sectional view of the internal structure of the sun. And now we might wonder, well, how do we know that the sun has this kind of an internal structure? Can we see down there? The answer is no, we can't. And so how can we tell that the sun actually has the kind of structure that we are indicating here? The answer is we look at the sun in terms of what are called vibrational patterns on the surface. And so these vibrational patterns are associated with the sun's surface rising and falling after solar explosions have taken place. Okay? And so here we can see that there are certain points in the sun's surface that are moving toward us, and so those would be the blue areas at this moment, And there are other parts of the sun that are moving away from us. Those are the red-shifted areas. And this is just for one mode of vibration. But it turns out that scientists have been able to detect 10 million different modes of vibration on the surface of the sun that are produced by events like solar flares. And so what we can do is a mathematical model of the sun to get the internal structure. So this is the process that we go through then, is we generate, to get the interior structure, we generate a mathematical model, we apply the known laws of physics to it, so we collect data from surface vibrations. This is called helioseismology, by the way. Or starquakes. So you collect data then from the surface vibrations, then you construct a mathematical model. And then you see whether your mathematical model fits the data. And usually it won't. So then you keep changing the model until it does fit the data. And there are ways of doing this with a computer called iteration procedures that get you closer and closer to the correct value. So this is data driven, but then we run through computer simulations, because a lot of these calculations would be too difficult for us to do by hand. And then we keep changing the model until the model and the data line up. Okay? And so going back then to this interior cross-sectional view, this is, put simply, this is like doing a CAT scan on the sun. Okay? And this is similar to what we've done on the Earth too, by measuring earthquakes on the Earth and the way that the interior vibrates, we've been able to determine the interior structure of the Earth. And so seismology is an important tool. But getting back to our internal structure of the sun, we have in the very center the core. So the core is where most of the fusion takes place, essentially all of it, is the most dense and actually is more dense than a metal on the Earth, even though the temperature is so hot. So this is where the fusion reaction happens. Then surrounding the core, we have what's called the radiation zone. And so here, the mass has been turned into energy, and that energy is in the form of what are called gamma ray photons. And so they're transported through this part of the sun by means of electromagnetic waves. So that carries the energy through the radiation zone. And then we get to the upper level of the solar interior. This is called the hydrogen convection zone, in which hydrogen flows like a fluid. So it's heated at the base of the radiation zone, and that material then moves up to the surface. At the surface, we're at 11,000 degrees Fahrenheit. So we're going from 27 million at the core degrees Fahrenheit to only 11,000 at the surface. So that's cool. So relative to where it's been. And so the fluid flows up, it cools, and then sinks. So it rises, it's like a buoyant fluid that rises and falls in these convection loops, which rise and fall like this, all the way around. And then that is what carries the energy of the sun from the core to the outside surface. Now we might wonder, how long does it take for the energy to get from the core to the surface? And we realize that once it gets to the surface, it takes about 8 minutes to get 93 million miles to us here on the Earth. But how long from the core to the surface? Well, something like 1 million years. And so the photons that are released in the core have to battle their way through and are constantly being re-radiated and knocked backward by all of the obstacles that are in the way. And so although it might take 1 million years for some of the energy that was produced to get all the way to the surface, there is some energy that was produced 64 million years ago in the center that is just getting to the surface now. And so when the dinosaurs were still around, some of the energy that's getting to us here on the Earth was produced inside of the sun. And so it's a long, arduous process for the photons of light to go from gamma ray photons, and then they're degraded in energy until, and this is a good thing for us too, because if they were just pure gamma ray photons, then life would be impossible on the Earth. The fact that they've degraded so much in energy, all the way down to now it's lower energy visible photons, that is what allows us to get energy from the sun in a way that doesn't create huge amounts of mutations, which would make life impossible. So nature seems to know what it's doing.